Mount Rainier towers over Washington state, majestic, snow-capped, and seemingly eternal. To many, it's more than a mountain. It's a symbol of calm and beauty on the horizon.
A swarm of small earthquakes rattled Mount Rainier this morning as we give you a live look at the mountain. The U.S. Geological Survey and Pacific Northwest Seismic Network says the activity started around 1:30 a.m.
Mount Rainier stands quietly above the skyline of Washington state, towering, majestic, snow-capped, and seemingly eternal. To many, it is simply part of the horizon, a postcard, a backdrop, a symbol of stillness. But in 2025, instruments buried deep beneath its slopes recorded something no one expected. The mountain moved. Not visibly, not violently, but unmistakably. A sudden increase in deep, long-period earthquakes, subtle ground uplift, and new gas emissions rising from vents near the summit crater have signaled a change inside Rainier's magma plumbing system. Scientists aren't saying an eruption is imminent, but they are saying the volcano has reawakened from a period of deep dormancy, and the systems inside are shifting again. The question now is not what has happened, the question is what happens next. Chapter 1. Mount Rainier, a sleeping giant, begins to stir. What if the most dangerous volcano in the United States wasn't Yellowstone or Mount St. Helens, but the quiet white mountain everyone assumes will never erupt in their lifetime? Because Mount Rainier has just shown signs that it is no longer asleep. Mount Rainier is not just another volcano, it is a stratovolcano, a towering cone of hardened lava, ash, and rock layers stacked over thousands of years. At 14,411 feet, it dominates the Cascades, both visually and geologically. Yet Rainier's true power isn't in its height, it's in what lies hidden beneath. A massive reservoir of magma, water-saturated rock, and glacial ice. Rainier contains more ice than all other Cascade volcanoes combined. And that is where the danger begins. Not with fire, but with water. Because if heat begins to rise through a glacier-covered volcano, the result is not simply lava, it is lahar, a fast-moving, cement-like flood of volcanic mud, rock, and melted ice that can race down valleys at highway speeds, reaching cities miles away. And lahars are Rainier's signature threat. But for lahars to form, heat must increase, pressure must build, magma must move. And in early 2025, that's exactly what researchers observed. The first sign, deep earthquakes. Seismometers recorded a cluster of deep, long-period quakes 20 to 40 kilometers below the summit, the depth where magma begins to pressurize. These weren't surface rock adjustments or ice quakes. Their waveform signature matched fluid movement, magma rising slowly. Deep quakes are the first stage of volcanic reactivation. The second sign, ground uplift. GPS sensors anchored in bedrock detected 3 to 7 millimeters of uplift across Rainier's summit region. Tiny, but consistent. Ground does not rise on its own. It rises when something beneath it expands. The third sign, gas output changes. Gas sensors recorded increased emissions of carbon dioxide, CO2, released when magma decompresses, sulfur dioxide, SO2, released when magma reaches shallow systems. These are not surface vent burps. These are messages from the magma chamber. So what does this mean? Not eruption, not evacuation, not panic. It means Rainier has shifted from dormant to active monitoring status. This is the phase where internal conditions change before external signs appear. Rainier is pressurizing, adjusting, moving. Volcanoes do not wake overnight. They stir, sometimes for years, sometimes for decades, building toward a decision the Earth makes on its own timeframe. What scientists fear is not lava pouring from the summit. What they fear is the water, because if even a small amount of magma reaches the base of Rainier's glaciers, the result will not be a mountain eruption. It will be a valley-filling wall of volcanic mud moving like a liquid bulldozer. Cities including Orting, Puyallup, Sumner, Tacoma, and even parts of Seattle's South Corridor lie in the direct path of Rainier's historic Lahar route. In other words, Rainier does not need to erupt to cause devastation. It only needs to heat up, and it has already begun. Chapter 2: Mount Rainier, the glacial ice that makes this volcano dangerous. If Rainier erupts, it won't be fire that destroys cities. It will be water, not rivers, not rainfall, but the mountain's own glaciers, melted in an instant and turned into a force more destructive than lava itself. Because Rainier doesn't need to explode to be catastrophic, it only needs to heat up. Mount Rainier is home to the largest single concentration of glacial ice on any mountain in the lower 48 states. More ice than Mount Baker, more than Mount Hood, more than Mount St. Helens ever had. These glaciers stretch across Rainier's flanks in thick, frozen rivers, some more than 700 feet deep, locked into place by cold and elevation. But glaciers are not permanent. They are only as strong as the temperature around them. When heat moves upward from Rainier's magma chamber, it doesn't instantly produce lava fountains. It first travels through layers of fractured rock and hydrothermal systems, natural pipes that conduct heat toward the surface. The first thing that responds isn't the rock, it's the ice. When glacial ice melts rapidly on a volcano, the meltwater has nowhere to go but down, and down Rainier's flanks lie deep, carved river valleys that channel water into deadly acceleration. This is how lahars form. A lahar is not mud, not slush, not simply water. A lahar is liquid earth, a concrete thick wall of boulders, soil, trees, and ice, moving at speeds that can exceed 60 miles per hour. It does not flow around obstacles, it erases them. Entire forests, bridges, rail lines, highways, neighborhoods, gone in minutes, not hours. Rainier has done this before. The geologic record is clear. 5,600 years ago, the Osceola Lahar buried much of present-day Auburn and Enumclaw under hundreds of feet of volcanic mud. 500 years ago, the Electron Lahar roared down the Puyallup Valley, leaving a debris field still visible today. These were not eruptions that destroyed cities. They were melt events, hydrothermal heating, water released, runaway collapse. The destructive power of Rainier comes from its ice. Why scientists are paying attention now. The recent seismic and gas activity recorded in 2025 is not happening near the summit crater. It is happening beneath the glaciers. That distinction is critical. When magma moves upward, it does not start at the top. It begins deep, where pressure forces molten rock to expand and heat groundwater systems. As heat rises, ice weakens, melt accelerates, water pressure increases inside rock layers. And once water pressure gets too high, rock fails. Not explosively, but catastrophically. This failure causes sudden glacial collapse, valley-scale flooding, rapid landslide movement that becomes a lahar, all without a volcanic eruption. In fact, most of Rainier's past catastrophes happened without lava ever reaching the surface. Why this matters for today. Downstream from Rainier lie some of the fastest growing communities in Washington state. Orting sits directly on top of ancient lahar deposits. Puyallup Valley farmland overlays volcanic mud tens of meters thick. Tacoma's port and industrial districts lie at lahar runout elevation. Warning sirens exist. Evacuation routes exist. Models exist. But evacuation time for a Rainier-generated lahar may be as little as 35 minutes. That's less time than most commutes, most school dismissal processes, most emergency coordination procedures, which means when Rainier moves, speed becomes the deciding factor. Rainier is not signaling eruption, it is signaling change. And when change begins on a glacier-covered volcano, water becomes the weapon. Chapter 3: Mount Rainier, the signals beneath the mountain. Volcanoes don't erupt without warning. They announce themselves, quietly at first, not in explosions, but in rhythms. A tremor here, a puff of gas there, a slow rise in the ground, almost too small to notice. And when these signs begin to line up, scientists pay attention because the mountain is speaking. Over the past several months, the monitoring network surrounding Mount Rainier has recorded an escalating sequence of geological signals. None of these signals, by themselves would trigger alarm, but together they form a pattern seen in volcanoes transitioning from deep dormancy into active internal reorganization. This is not panic, this is observation. Let's break down the 3 signals now advancing beneath Rainier. 1. Deep long-period earthquakes, DLPs. Most small earthquakes, the ones you see on public seismographs, are caused by rock breaking, but DLP earthquakes are different. They are slow, rhythmic pulses generated by magma moving through deep rock like pressure waves in a pipe. Rainier has now produced clusters of DLP quakes between 20 and 40 kilometers below the summit, the depth of the upper mantle and lower crust interface. This is the magma staging zone, where molten rock begins its journey upward. When DLP activity increases, it means heat is rising, pressure is redistributing, the magma system is adjusting. 2. Ground uplift. The mountain is rising across Rainier's upper flanks. High-precision GPS stations track elevation changes to within a fraction of a millimeter. Beginning in early 2025, these stations detected a steady vertical uplift of 3 to 7 millimeters, concentrated near the summit dome. This is not landslide movement. It is not ice melt expansion. It is internal expansion, the mountain swelling from within. When magma pressurizes underground chambers, the surface above responds like a slow, silent balloon. Mountains do not breathe unless something is pushing from below. 3. Changing gas emissions. The mountain is venting. One of the clearest signs of magma movement is gas release. Gas sensors have detected rising levels of CO2, carbon dioxide, indicates magma is losing pressure at depth. SO2, sulfur dioxide, indicates magma is reaching shallower rock. H2S, hydrogen sulfide, signals changes in hydrothermal systems. Normally, Rainier's summit emits low levels of volcanic gas, the legacy of its warm acidic crater springs. But now, gas ratios are shifting. CO2 is increasing fastest, meaning pressure is changing deep inside the system. SO2, though lower, is appearing more frequently, meaning gases once trapped are now finding pathways upward. This does not mean magma is close to the surface. It means the plumbing system is being reconfigured. Just like a city's water pipes rattle before forcing pressure into a new line, Rainier is adjusting its internal flow. Why scientists are concerned? Now the signals are coordinated. Deep quakes, heat rising, ground uplifting, gases venting. This is a chain reaction, not coincidence. Again, this is not eruption behavior, but it is pre-eruptive reorganization in the earliest stage. The danger is not that Rainier will erupt tomorrow. The danger is that conditions are now changing, and once a volcano begins to change, it rarely reverses course. Volcanoes do not go back to sleep. They slowly build toward a decision, and Rainier has just begun to choose. Chapter 4. Mount Rainier, the Lahar threat and the cities in its path. When people imagine a volcanic disaster, they picture ash clouds or rivers of glowing lava, but that's not what makes Mount Rainier dangerous. Rainier's greatest threat is invisible, silent, and already in place. A catastrophe that can begin without any eruption at all. A disaster that can reach cities while the mountain remains standing in perfect white stillness. Because when Rainier moves, even slightly, it can unleash lahars, and lahars are unlike anything most people have ever seen. The nature of a lahar. A lahar is not mud, not water, not lava. A lahar is the mountain liquefied, a roaring torrent of melted glacier, pulverized rock, shattered trees, and boulders the size of houses, flowing with the speed of a highway vehicle and the weight of concrete. Lahars do not flow around obstacles, they erase them. They fill river valleys, they bury landscapes, they reshape the map. If Rainier's internal heat rises even modestly, enough to melt just a portion of its vast glacier system, a lahar could form in minutes, without a single plume of ash appearing in the sky. Rainier's lahar highways. Rainier's flanks are carved by deep valleys, natural chutes that direct lahars straight into populated areas. These are not theoretical paths. They are already mapped. The Puyallup River Valley leads directly to Orting, Sumner, Puyallup, and Tacoma's industrial corridor. The Carbon River Valley. Carbon River Valley threatens Carbonado, South Prairie, and Buckley. The White River Valley runs towards Enumclaw, Auburn, and Kent. These are not remote wilderness towns. These are suburbs of Seattle. Over 290,000 people live in zones mapped as historical lahar flow paths. How fast would a lahar travel? Past lahars tell us the answer. The electron lahar traveled over 60 miles in a matter of hours, long before modern cities existed. Today, with more development and more people, a lahar from Rainier could reach Orting in 35 minutes. 35 minutes. Not enough time for traffic, not enough time for hesitation, barely enough time to move on foot. This is why Orting has lahar evacuation sirens. This is why schools practice running, not driving, to high ground. This is why Rainier is considered the most dangerous volcano in the United States by the USGS, not because of eruption power, but because of lahar reach. The modern risk. Rainier does not need to erupt to create a deadly lahar. It only needs 4 conditions. Magma warms the hydrothermal system. Ice begins melting faster than it can refreeze. Water builds pressure in weak volcanic rock. A section of the glacier or slope collapses. When all 4 occur, the lahar begins at the summit and accelerates instantly. No warning, no visible signal, no time to prepare after it starts. This is why monitoring matters. This is why scientists are watching closely. This is why the recent changes cannot be ignored. Rainier is not just a volcano. It is a system of fire, water, rock, and gravity, balanced delicately above countless lives. And now, that balance is starting to shift. Chapter 5. Mount Rainier. How scientists detect when a volcano is about to change. Volcanoes rarely erupt without warning. They signal long before anything appears at the surface. Subtle shifts that reveal changes deep within. Scientists watching Mount Rainier are not looking for visible explosions. They are listening for the mountain's quieter language, patterns of tremors, pressure changes in the rock, and small variations in heat and gas. Rainier does not announce itself loudly. It changes slowly, and those trained to observe it can see the shift beginning. Mount Rainier is monitored by an extensive volcanic watch network, operated by the USGS Cascades Volcano Observatory. Using seismic instruments, GPS sensors, satellite imaging, gas analysis, and thermal monitoring, researchers track how the volcano moves and breathes in real time. One of the early signs now appearing is an increase in deep, long-period earthquakes, the kind formed not by cracking rock, but by magma moving at depth. These are the earliest indicators of internal pressure reorganizing. At the same time, GPS and satellite measurements have detected slight uplift across Rainier's summit region, only a few millimeters, but enough to show that something beneath the mountain is expanding. This is not surface instability, it is a quiet internal swelling as the system adjusts. Gas emissions tell a similar story. Increased carbon dioxide and intermittent sulfur dioxide suggest that new pathways are forming within the volcanic plumbing system. The magma is not rising towards the surface, but the routes it could use in the future are being reopened. Thermal surveys and subglacial acoustic sensors have also detected small increases in heat and changes in meltwater flow beneath Rainier's glaciers. These shifts matter because water, not lava, is often the trigger for the volcano's most destructive events. Taken together, these signs reveal a consistent picture. Rainier is not erupting, but it is changing. The volcano is moving out of deep dormancy and into the earliest stage of internal reactivation, a phase that can last years or decades. Scientists are not sounding alarms, they are paying attention. The mountain is no longer resting, and now so are we. Chapter 6. Mount Rainier. What the past reveals about the future. To understand what Mount Rainier may do next, we look to its past. The landscape surrounding the volcano is shaped by earlier events, layers of ash, buried forests, and valley-filling mudflows that remain preserved beneath towns, fields, and neighborhoods today. These are not just remnants, they are records of how Rainier behaves. Most of Rainier's most destructive events were not explosive eruptions, but lahars, massive mudflows caused when heat or structural collapse melted glacier ice. About 5,600 years ago, the Osceola collapse sent a lahar that buried large parts of present-day Enumclaw and Auburn. Around 500 years ago, the electron lahar flowed down the Puyallup Valley, leaving deposits that now lie directly beneath the town of Orting. These disasters happened because water and ice were destabilized, not because magma reached the surface. Today, the same valleys that once carried those flows are filled with homes, roads, businesses, and schools. The paths have not changed. What has changed is what now stands in them. Rainier does not shift quickly. The process is now being observed. Rising heat, internal pressure changes, and subglacial water movement happens slowly, but they follow the same early patterns seen before past lahars. This does not mean an eruption or collapse is coming soon. It means the volcano is active, not silent. Scientists are not warning of immediate danger. They are urging awareness. Rainier is offering information in real time. The past shows what Rainier can do. The present shows that the system is moving again. What happens next depends on how closely we pay attention.